Hi, I'm Morgana and welcome to PC2. The aim of this experiment is to determine Planck's constant using the photoelectric effect. The photoelectric effect is when a light particle ejects an electron from a metallic surface. So that's what we'll be doing here. With the equipment, we have a mercury lamp that is shining through an aperture that is going through a lens and shining onto the face shield, which has a shield here and is shining into this sensor. This sensor is hooked up to a multimeter, which is measuring the voltage that the electrons are ejecting. Now, the first thing you want to do is set it up. This is the first part. So we turn it on and we wait for it to warm up for a few minutes. Then we align this so that we get a bright light. Here it is. It should be aligned with the hole there. Now, we turn the thumb screw on the lens so that it is loose on the two rails. And we move it such that we get the sharpest image possible on that line, about here. We turn the thumb screw again to fix it securely. Now I move the shield back and I go ahead and turn the sensor on. Now, I need to read some voltage measurements, so I'm going to turn it on to DC voltage. And there's a reading on there already. Right, I'm going to move this to a yellow line. Here's one. And affix the yellow filter onto the shield. I make sure I don't get any fingerprints on it because it's very sensitive. And now I'm going to hit the push to 0 button on here. And that pushes this to 0, and then it will get a voltage measurement. When it's stable, you read the measurement and put it in your proforma. Cool, then we take the lens off, the filter. Then I move it to the next line, which is green. So I grab the green filter and affix it on magnetically there, and then I hit push to 0 again. When the voltage measurement's stable again, at about 0.72 something, there we go. I write that down in my proforma again. I repeat the same procedure for the next 3 lines. Oh dear, I see they're a bit fuzzy, so I'm going to move the lens again. There we go, now I can see 3. Here's the blue line. I do not put a filter on this line, so I push to 0 again and take the measurement, 1.36-ish. Then I repeat for the violet line, which is in between. Hit push to 0, and it's about 1.53. So I push this to the ultraviolet line now, which is the 3rd and final line in that series. Hit push to 0, and I read the voltage measurement again. And now I have all my data for the first graph, and that will be on the board. As you may see in your prac manual, there's a derivation of the equation you will be using. What's going on is that we're equating the kinetic energy to the stopping potential, and then we're equating that kinetic energy also to the energy of a photon, because we know they're photons now. Then we will, because we're measuring stopping potential as a function of frequency, we must rearrange it to reflect that. So what they've done in the manual is taken W0 away and divided by E. So that's how they got this equation. In the experiment, as you just saw, we were measuring the voltage at certain frequencies. This is not a V, it's a Greek letter nu. It looks an awful lot like a V, but be careful there. You could write F if you were getting too confused. So this is a straight line, the theory says. So which parts of these are Y and which is M and which is X and which is C? This part is our dependent variable, so it is a Y. This nu is our frequency, and that's what we're changing, the colors of the light. So that is our X, which means anything next to it must be our slope. And that's what it means on the graph in your manual when it says that your slope is h on e. And the remaining stuff, negative W naught on e, is our intercept. So when it says to calculate Planck's constant from the slope, what it wants you to do is extract the slope from your graph and then equate it to h on e. Slope is h on e, therefore h, Planck's constant, is, m, the slope, times e. And that's what you have to do to find Planck's constant. Now we also want to know what W naught is. So we grab our intercepts from the graph, which is down here, and we equate it to negative, don't forget the negative, W naught on E. And then we rearrange that for W naught, which is negative the intercept times E. And that's how you find the values that they asked for. Right, it is time for the second part of the experiment. In this part, we'll need to align the shield with the ultraviolet line, and then we'll be using this transmission filter. This transmission filter has different levels of transmissions. There's 20%, 40%, 60%, 80%, and 100%. In this bit, we'll be using the 100% transmission. So I'm aligning that with the hole there. Then, just as before, but this time with the stopwatch ready, I'll be hitting push to 0 and then timing how long that takes to stabilize. And then we repeat that for the 60% transmission and the 20% transmission. Thank you for joining me, and I hope you got something out of that.